Hello, folks. All right, chap. So in today's lesson, we're going to look at proofs of compound and double angles. I've already created a video about this stuff, but here we're going to look at their proofs in a slightly different way. eh? So for any two angles A and B, we can prove that cos A minus B is equals to cos A cos B plus sin A sin B. So that's your first compound angle. Then cos A plus B is equals to cos A cos B minus sin A sin B. Notice, guys, that whenever we're using cos, if there's a minus between two angles, when you expand, you're going to put a plus. If it's a plus, when you expand, it's a minus, and that works for cos. Sin, if it's positive, it's positive. It's negative, it's negative. So sin A plus B is sin A cos B plus sin B cos A. And A minus B is sin A cos B minus sin B cos A. Right. So let's look at proofs. Okay. So if we given these two diagrams, right? So we can try and find AB using the distance formula and also using the cosine formula. And then if we do that, you'll end up with an expression. And then if you equate those two expressions, and then you divide by the constant -2, then you're going to get this. So you can see that it's more or less the same as the one that I did in the previous video. And mind you, we are using the unit circle here. So because this is a unit circle, the radius is 1. Then we can use cosine subtraction formula to prove that cosine alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta. So how do we do that? Instead of writing plus beta, we write minus beta, right? And then from there, if we then expand, and remember that for negative angles, cos of a negative angle is equal to cos of that angle. And sine of a negative angle is negative sine of that angle. So cos alpha plus beta will then be equals to cos alpha cos beta minus sin alpha sin beta. Then for sine, we know that cos 90 minus beta is equals to sin beta, and sin 90 minus theta is equals to cos beta. Therefore, it means if we have sin alpha plus beta, we can write it as cos 90 minus alpha plus beta. This we can write as cos 90 minus alpha in brackets, then minus beta. We're using the associative law here. Then from there, we can expand this using the cosine subtraction formula. Then from there, if we apply our cofunction relationships, then cos 90 minus alpha is sin alpha, sin 90 minus alpha is cos alpha. And so sin alpha plus beta is equal to sin alpha cos beta plus cos alpha sin beta. Again, we can use the sign addition formula to prove that sin alpha minus beta is equal to sin alpha cos beta minus cos alpha sin beta. How do you do that? Instead of writing a plus, we write a plus using a negative angle. So this becomes sin alpha plus negative beta. If we expand that and use the knowledge of our negative angles, Then we get that sine alpha minus beta is equals to sine alpha cos beta minus cos alpha sine beta. Now, consider cos alpha plus beta equals to cos alpha cos beta minus sine alpha sine beta. And then, so these are the two angles that we just proved. Now, what happens if we then say alpha is equals to beta? Then it means for this one, cos 2 alpha will then be equals to cos squared alpha minus sine squared alpha. But we also know that sine squared theta plus cos squared theta is equals to 1. Therefore, it means that cos squared alpha minus 1 minus cos squared alpha. So instead of writing sine squared theta, we wrote this as 1 minus cos squared alpha. Then if we simplify that, you get 2 cos squared alpha minus 1. Or we can instead substitute cos squared alpha with 1 minus sine squared alpha. And then that will leave us with 1 minus 2 sine squared alpha. So cos 2 alpha is equals to 1 minus 2 sine squared alpha. Also, sine 2 alpha is equals to sine alpha cos alpha plus cos alpha sine alpha. And then if you add these two things because they're the same, we get 2 sine alpha cos alpha. So these are your double angles. Right. So we have cos 2 alpha is cos squared alpha minus sine squared alpha. 2 cos squared alpha minus 1. 1 minus 2 sine squared alpha. 3. And then for sine, we have 2 sine alpha cos alpha. Then let's prove the identity for the tangent function. So we have tan alpha plus beta is equals to tan alpha plus tan beta over 1 minus tan alpha tan beta. Again, here, if this is plus, then the numerator will have plus and the denominator will have minus. However, if this was subtraction, the numerator will have subtraction, the denominator will have plus. Yeah. So to prove this, we're going to look at the left-hand side. So the left-hand side is tan alpha plus beta. We know that tan can be written as sine over cos. So it's sine alpha plus beta over cos alpha plus beta. Then we expand those, right? Then from there, we divide every term by cos alpha cos beta. So we're going to divide by cos alpha cos beta. And why are we choosing that? Because we want to end up with 1 here. And if you notice, cos alpha cos beta is in the position where you want to end up with 1. So we're going to divide by it. Divide every term by this. And so if we do that and we simplify, we get, so you can see cos beta and cos beta cancels out. Cos alpha cancels out. And then cos alpha cos beta over cos alpha cos beta will cancel out. And then here, sine alpha over cos alpha will give us tan alpha. Sine beta over cos beta gives us tan beta. Yeah. Sure. Then we also have half angle formula for cos and sine. So we know that from cos 2x equals to 2 cos squared x minus 1, we can deduce that if we take negative 1 to the left and then we divide both sides by 2, then we end up with cos squared x is equals to 1 plus cos 2x over 2. Now an example would be cos squared 15 is equals to 1 plus cos 30 over 2. And then remember that cos 30 is root 3 over 2. You simplify that, you get 2 root 3 over 4. Then cos squared 22, 5 is equals to 1 plus cos 45 over 2, right? So yeah, and then for sine squared x, we get 1 minus cos 2x over 2. Yeah. And then these are your examples. Okay, so now if we take the sine, if we take sine x plus y and we expand it, and sine x minus y and we expand it, if we add those two equations, right, we'll end up with 2 sine x cos x, because negative cos x sine y will cancel out with positive cos x sine y. So you'll end up with sine x cos y plus sine x cos y, which is 2 sine x cos y, right? And then this side, this plus that will just give you that. Then if we divide both sides by 2, we end up with sine x cos y is equal to sine x plus y plus sine x minus y over 2. Similarly, we can do the same with cos. Yeah. All right, folks. So now I want you to pause the video, try and prove the following formulae, and then we'll continue from there. All right, hello, folks. I hope that you were able to try these questions. I mean, even if you couldn't do some of them, at least try. At least try. So for number 1, I think we've already looked at this one. Yeah. So yeah, very straightforward. Very straightforward. Then number 2, it's the same as the one we did. However, now what we do is that instead of writing x plus y, we just write beta plus beta. So this becomes tan beta plus tan beta over 1 minus tan beta tan beta, which will then give you 2 tan beta over 1 minus tan squared beta. Then number 3, again, I think we've already looked at these ones as well. And then lastly, number 4, we also looked at this one as well. All right, folks. So what I want us to do now is to look at applications of these formulas. Yeah. So, okay. So this is an example of application of double angle formula. Yeah. If tan theta is equal to negative 4 over 3, right, and theta is between 180 and 90 degrees, evaluate these things. First thing first, remember that if we have tan theta is equals to a fraction, the numerator is your y, then your denominator is your x, right? So this means that we have y over x. However, we don't know which one is negative, because 4 over 3 is negative. So not that's negative 4 over 3 or 4 over negative 3. So to check which one is negative and which one is positive, we have to look at the restriction. Now for the restriction, we are told that we must focus on the quadrant where our angle is between 90 and 180. And that quadrant would be quadrant 2. So what's going on in quadrant 2? In quadrant 2, we know that y is positive and x is negative. So what that means is that for is going to be positive and 3 is the one that is negative. So afterwards, you then draw your diagram. Then -3, then 4. Now to get the hypotenuse, we use the theorem of Pythagoras. 4 squared plus -3 squared, that is 16 plus 9, which is 25. And then you take the square root of 25, you get 5. Right? So that's it. Now that you have all the sides of your triangle, then you can start answering the questions. So sine 2 theta is equals to 2 sine theta cos theta. Then from there you can substitute. We know that sine is opposite over the hypotenuse. So it's 4 over 5. Cos is adjacent over hypotenuse. So that is -3 over 5. Then you simplify that, you get your answer. Cos 2 theta is equals to 2 cos squared theta minus 1. Then you substitute cos, we said it's -3 over 5 squared minus 1. Then get your answer. Then for number C, tan 2 theta is equals to 2 tan theta over 1 minus tan squared theta. Substitute that, and then you get your answer. Then you can check whether cos 2 theta is equals to this, and that will give you the same final answer. Now let's check problem number 2. So this is the question. Calculate sine 26 in terms of k if sine 13 is equal to k. Now this question is similar to the one that we did previously, because now 13 degrees, or let's say, yeah, 13 degrees is an angle between 0 and 90 degrees. So this is in the first quadrant. That's step number 1. And then number 2, if you just give a k, we can write k as k over 1. Why do you want to write it as k over 1? Because we want to write it in such a way that it gives us opposite over the hypotenuse. So if the opposite is k, 1 is going to be the hypotenuse. All right. So you draw your diagram, then we have k as being the opposite side, 1 is your hypotenuse. And then we use the theorem of Pythagoras to find the adjacent side. Right? Remember, adjacent will then be equals to the square root of 1 minus k squared. Now, then from there, now that you have all the sides, then we can start answering the question. Now notice that sine 26 is actually equals to sine 2 times 13. And because of that, this is then equals to 2 sine 13 cos 13. And then we know that sine 13 is k, cos 13 is root 1 minus k squared over 1. So if you multiply those two things, we then get 2k root 1 minus k squared. That is your answer. Then number 3, without calculators, use standard angles to calculate cos 75. So whenever they say do not use your calculators, we know that we have to use these two massive triangles. So from here, we know that, okay, cos 75 can be written as cos 45 plus 80. Then if we expand that, it's cos 45 cos 80 minus sine 45 sine 80. Sine 45 is opposite over adjacent. All right, cos 45 adjacent over hypotenuse. Cos 80 is adjacent over hypotenuse. Then sine 30 opposite over hypotenuse. If you do that, then notice that your denominators are going to be the same. Then you just subtract your numerators. So you get root 3 minus 1 over 2 root 2. Okay. Now, let's try this one. Express as a single trigonometric expansion. A were given sine 4 alpha cos 3 beta plus cos 4 alpha sine 3 beta. This is just sine 4 alpha plus 3 beta. And B just gives us cos 2a plus 3b. And C gives us tan 50 minus 30 minus 20, which is tan 30. And tan 30 is equals to 1 over root 3. That is according to these diagrams. So it's opposite over adjacent. 1 over root 3. Okay, let's now use double angle formula to simplify this. So you have 2 sine 4 theta cos 4 theta. This is equals to sine 8 theta. Right. Then 2 cos squared 35 minus 1 is equals to cos 70. 2 tan 50 over 1 minus tan squared 50 is equals to tan 100. And then these are the formulas we use to find the answers here. Then, number 6, use where applicable compound and double angle formula to factorize these expressions. A, we have sine x cos 34 plus cos x sine 34. All right, this gives us sine x plus 34. So we write it as a monomial. But remember, a monomial is just one term. Then B, the first thing that we do is to remember, guys, that sine squared x plus cos squared x is equals to 1. Yeah? So if you take 1, if you take cos squared x to the right and you take 1 to the left, then you're going to get negative cos squared x being equals to sine squared x minus 1. So negative cos squared x is actually sine squared x minus 1 plus 4 sine x plus 4. Then from here, simplify that, it gives you sine squared x plus 4 sine x plus 3. Then this is a trinomial which we can factorize as sine x plus 3 times sine x plus 1. Okay, example number 7. Find the irrational value of cos 22.5. Remember that cos squared 22.5 is equal to cos 45 plus 1 over 2 from this half angle formula. And from there, you can substitute your stuff. Right. And note that this is not equal to negative the answer. Now, obviously, because 22.5 is in the first quadrant, and in the first quadrant, all trigonometric ratios are positive. So you can't have something that is negative. Okay, folks. Now, please pause the video and try this exercise. Folks, calculators may not be used. Do not use a calculator. I repeat, do not use a calculator. Hello, folks. Hey, I'm sure this one took more than an hour, man. But I'm glad we were able to try it. Number 1 and number 2, the answer is 1 minus root 3 over 2 root 2. And then sine 195 gave us 1 minus root 3 over 2 root 2. Sharp. Remember, folks, son, 180 plus 15, 180 plus is in the third quadrant. And we know that only tan is positive. So this is negative sine 15. You could have also done this thing using cos 90 plus 15. Cos 90 plus 15 will then give you negative sine 15. And then negative sine 15 will give you the same thing. And then with this one, again, you could have written it as sine. So sine 19195 is equals to sine of uh, 90 plus, it's going to be 90 plus what? 105. Yeah. Which will then be cos 105. So yeah, either way. Then for number two, 2a gives us sine 7b beta minus 5 beta, which is sine 2 beta. Then b gives us tan beta plus 20 degrees. Then for c, 1 minus 2 sine squared 2 beta gives us cos 4 beta. And then b gives us tan 12x. Then for a, we get cos x minus 20. Then b sine x plus 2, sine x minus cos x. Lastly, we have tan 22,5 degrees being equals to negative 1 plus root 2. And we took this one and not the other one because this one gives us a positive value, which is what we want because 22,5 is in the first quadrant and tan is positive there. Yeah. So with that being said, thank you so much, folks. So in the next lesson, we're going to use compound and double angles formulae to prove some identities. Thank you.